Okay, hello everyone, and welcome to ModuleWorks webinar about our dental component. As you know, the dental market is developing quite fast, and that's why we would like to present our newest developments in this segment to you. Let me quite briefly introduce today's presenters to you. First of all, we have Mr. Niren Deshmukh, our dental project manager at ModuleWorks. Hi, Niren.
Hello all.
Hi there. And my name is Jens Weissel. I'm responsible for ModuleWorks marketing. And now I will just give the word to my colleague Niren, who will start out giving you a quick overview of what he will be talking about in the next 30 minutes. So Niren, the audience is yours. Just go ahead.
Yeah, so today we are going to demonstrate the features of ModuleWorks Dental Framework, which is a software component which runs behind the scenes of nesting software, which is used for dental manufacturing of crowns, bridges, telescope inlays, and different type of dental indications. So for today's demonstration, we will be using nesting software from one of our dental partners. So we are going to use XCAD's CAM solution, that's XCADCAM. So on the screen you see here XCADCAM interface. So we will nest a block and then put some indications here and then calculate the toolpaths. So the first thing we need to do is register a new block. Here you can see the block options you have depending on the machine you select. So you can predefine block shapes, block sizes. So we are going to use a 25 mm zirconia blank, a cylindrical one. We put the shrink factor here that's needed for zirconia. So we accept the blank. Now we can import dental indications. So this is the nesting queue you have, so you can see different jobs that are saved from the CAD software, or you can also import STL files for nesting into the software. So these files are from XCAD, so you can directly click on them and they appear in the block. So you can move these parts, or you can rotate the parts and place them. You see the support pins are generated automatically. But you can also modify the support pins. So you can delete some pins or add new ones. And you can also have an option to modify the support diameter, or to say whether you want to keep the pin after milling the indication. So you can say cut by machine. And then it also gives an option if you want to cut the whole pin or you want to partially cut it. So it gives you a percentage how much you want to cut the pin. So once you have placed the indications in the right position, you can go to toolpath calculation. So the toolpaths are calculated on predefined templates. So these templates are based on the material types and different indications, like crown, bridges, inlays, abutments. So you can have different templates for each of this indication and have a different sequence of toolpaths. So the nesting software automatically selects the right template for you. So you can either mill all the indications on the blank or selectively start calculation for one of those. So the toolpaths are calculated in parallel. So if you have a dual core or quad core, then they will be calculated on different CPUs. And at the end of the calculation, you will get an NC program, which you can send directly to the machine or put it to the nesting queue. So that's a NC program to run on a Roland machine, DWX50. Now we can see what toolpaths are generated in the background. So we have some pre-calculated toolpaths which we will load into ModuleWorks sample integration. So that's the user interface of ModuleWorks sample integration, and we can visualize the toolpaths here. So on this blank here we have different indications. So we have a full anatomic crown here, a telescope, a 5-unit bridge which also has different insertion directions, abutment, inlay bridge, and a screw return bridge. So now we will go ahead and see the sequence of toolpaths that is used for anatomic crown. So on screen you see offset-based roughing, which will clear out most of the blank. So this is from the cavity side. We'll have the same operation from the occlusal side. So on the other side of the blank. Then we have some rest roughing toolpaths for a smaller tool. Next operation is for margin area finishing. For finishing inside the cavity, we have a constant cusp toolpath, which gives an equidistant step over. So this toolpath gives the best surface quality and the best fit for a crown. Also on the outside, we are using constant cusp toolpath because our trials have showed that it gives the best surface and the fastest machining time. So after finishing on the occlusal side, we will also mill the fissure areas here with 0.6 tool. So that's a fissure finishing toolpath here, you see in the screen. The next dental indication here is a telescope. So the sequence is similar to a crown, but here on the telescope we have a different insertion direction to the direction of the telescope on the occlusal side. So we have an additional toolpath here that will rest rough inside the cavity using the insertion direction. Then again we have finishing, which we can simulate here. So you can see that it's index milling. So it's again in 3+2 axis direction. Next we have finishing on the outside of the cavity and finishing the occlusal side. And we have some rust finishing operation. Next we have an abutment. This abutment has screw holes which have different direct insertion directions from occlusal and cavity side, and this insertion directions are automatically picked by the CAM software, and the toolpath for screw holes are generated in this direction. So we have the normal roughing, we have overall finishing on the cavity side. We kept the screw holes so that the tool doesn't plunge into the hole while finishing this. Now the CAM kernel from ModuleWorks, apart from generating the toolpath, it also generates the support geometries required for optimal toolpath. So we generate the wing surfaces, we also generate some capping surfaces. So here you can see that we generated the capping surface for finishing, and now we are roughing inside the screw hole. We have some finishing cycles for the screw hole and then finishing outside. Again, we have overall finishing on the occlusal side here with the cap screw hole, and then 3+2 axis roughing to the screw hole. Next we have here is 5-unit bridge. So in zirconia, sometimes we need a stabilizer for sintering. So this bridge here, we have it along with the stabilizer. So on the cavity side, we are roughing also the stabilizer region, but on the occlusal side, we'll leave out the stabilizer so that during the sintering, it can rest on the stabilizer. We have some rest roughing operation. You can notice that we have left this indication out for the rest roughing. This is automatically left out because this scoping has an insertion direction of, there's a difference of 15 degrees. So there will be a lot of rest material remaining in the insertion direction. So we have a separate rest roughing operation automatically generated for this. So this logic can be built in the templates. Next we have margin area finishing. So you can see here that each margin area is milled in its own insertion direction for each coping. And then we have finishing inside the coping, which is also along the insertion direction. So we can simulate this toolpath here. So it starts with 3+2 axis. If there are any cement caps in, if there are any undercuts in the cement cap, then it will do a continuous y-axis motion. So here we save a lot of time by doing just continuous y-axis in the undercut regions, and then you can see it goes back to 3+2 axis. We have similar toolpaths for the rest of the cavities. Overall finishing for the bridge, for the milling the pontics and the connector. And then finishing the whole bridge from the occlusal side. Next we have a screw retained bridge. The operations are similar to the bridge we have seen. The only difference is we have kept screw holes, and we will generate separate toolpaths for the screw holes. Then we have here a pin trimming operation. You can see all the pins are trimmed out. Next we have operations for the inlays here. And last is inlay bridge. You can have also here inlay bridges with partial or full grounds or pontic, so you can have a complex inlay or onlay, and we have templates also for this. So we can simulate this in the verifier, and at the end we can see how the milled blank will look. So while it's simulating, we'll have a look at the grinding toolpaths. So we have developed a number of grinding toolpaths to mill glass ceramics. So materials like Vita blocks or Emacs, which can be grinded using diamond coated tools. So we'll see different approaches here. So we have 3 dental indications nested in 3 different positions. So the first toolpath we have here, the first approach is a trochoidal toolpath along the profile of the part. So we will simulate this toolpath here, so you can see that it trims out the block and only the part region is kept. The next operation is roughing and finishing inside the cavity, so that's one toolpath here. So we use a helical ramp, and then we use spiral outward motion to rough and finish this part here. So we can simulate this again. Then we have roughing operation for the material that's left over the pins from both directions. The next toolpath is a spiral constant cusp toolpath from outside to in. So that would rough and finish the occlusal side. Simulate this toolpath here. Because the grinding tools can only remove material using its sides, so it's more efficient milling with the sides. We have the cycles which are dedicated for this. So we'll also see other cycles doing the same, so we move from the ordering, it's always from out to in. We have a similar cycle on the cavity side. Then we can have a special cycle for finishing the margin area. For the next dental indication, we will have a different approach. So we have a zigzag toolpath which starts on the front side of the block. Then it moves to the back side where the pin is located. Now here you can see that when the tool engages on both sides of the cutter, we generate multiple depth step cuts. so the tool is not overloaded and burnt out. For the occlusal side, we use a different approach because we are using a conical tool. We are moving from the side and doing just the up milling. And we'll have the same from the other side. For the third part, we have a different cycle, which is like a U-shaped cycle, which will mill from the three sides of the block towards the center. So we have capped the cavity here. So this is roughing only on the outside, and then we will have a different tool path to rough and finish inside the cavity. We have a similar U-shaped cycle on the occlusal side. For this particular indication, you can see that this has 4 deep cavities, and we can't just ramp into the center and move outwards here, because when the tool plunges into these cavities, it will just burn out. So what we have here is a toolpath where we ramp into the 4 deepest points, and then we have ordering for opening up the 4 pockets. So we can simulate this toolpath here. So that's ramping and creating pockets. And then it's opening up each pocket individually. So based on different materials and different tool geometries and length of the tool, we have different approaches to grind dental parts. Also based on machine kinematics, we have different tool paths for 4-axis machines and 5-axis machines, so we can do rotary grinding and also 5-axis grinding. Now we can see, we move back to the milling toolpaths and see how the blank looks like after all the toolpaths are completed. That's a whole nested blank. So yeah, we have been developing a lot of new strategies and technologies, and we would be more than happy to share it with you. You're invited to our IDS booth, or if you can mail us if you want some more information.
So yeah, excellent. Thanks a lot, Niren, for this detailed insight into some of our latest developments. As Niren already said, there's a lot more to say about our dental component, but this webinar was just meant to give you more of a general impression of what we are capable of doing. Yeah, as Niren also said, a great chance for you to learn more about our dental component is the International Dental Show IDS in Cologne, Germany, which will open its doors on March 12th. We will be exhibiting, and we will be happy to give you some detailed demos of our component and answer any questions you may have. It's a great opportunity actually to get in touch and to get a good idea of what we can do for each other. If you're not able to attend the trade fair, I would like to point you to our newest dental fact sheet. Simply go to ModuleWorks.com, choose the Industries menu and select Dental to download our updated dental fact sheet, which actually summarizes all important features of our dental software. Anyway, if you have any questions, you can contact us anytime, of course. Just send an email to info@moduleworks.com. Visit our website or just give us a call. Also, please note that we have our own blog, we have a Facebook page, and we are also represented on Twitter, Google+, and YouTube, where you will find lots of valuable videos about our software. On YouTube, you can also find recordings of past webinars, and if you check in a couple of weeks, you'll find this webinar on YouTube too. So, having said this, I would like to close this webinar for now and thank you for your attention and thank my colleague Niren for sharing his expertise. Thanks and hope to see you at our next webinar. Bye.